All right, new perspectives on Geproci sets. Go for it, Jake.
Hi, I'm Jake. It's great to speak here for my first time at Colorado. And like Chris said, I will be giving a talk on the Geproci property and some new results of Geproci sets that I was looking at for my dissertation in Nebraska. So to start, what the heck even is Geproci? Because this is not a word that people are used to hearing. So we will say that
It's not Italian.
it's a mashup.
It sounds Italian.
It sounds Italian. That's where the shit comes from. Yeah. But if you have some collection of points, Z, a finite set in n-dimensional projective space, it'll be called Geproci if the projection, the image of the projection from Z onto a hyperplane from a general point P is a complete intersection. So Z is itself not necessarily a complete intersection, but its image projecting onto a hyperplane will be a complete intersection generally. And again, by a general point, I mean the collection of points that have this property forms an open subset in the Zariski topology and is therefore dense. So Geproci stands for general projection is a complete intersection.
So any set in P2 is Geproci?
I guess so, yeah. Yes.
Nonsense. Okay.
So I guess I should say that, yeah, I guess that would be a more, trivial example, but really we only know examples, really, for n equals 3 other than things that may have already started off as complete intersections to begin with. It's not as interesting. Yeah.
Wait, so it's a finite set of points
Yeah.
in Pn,
Yeah.
and you're projecting it onto a hyperplane, and that being a complete intersection, does that just mean all the points are distinct? Or what
No,
does
that means that the codimension is equal to the number of generators that carve out that number of points. So, for example, in the plane, you have, actually, there's my demonstration.
Yeah, I mean,
like this.
I'm thinking of like you have a bunch of points in the plane and you're projecting them onto a line.
This should be clickable.
What does that mean?
Okay, it's not clickable.
Okay.
But yeah, if you have, say, 9 points in the plane, they are a complete intersection if they are
they are a complete, okay.
the intersection
They
of two
are a
cubic
complete
curves.
intersection of other things.
Yes.
That's what I
Yes.
was missing
Oh,
that.
sorry.
Like, what is, okay, now I get it.
Yes.
I was thinking like somehow the intersection of the projection with something else is a complete
Oh,
intersection
no,
with
no.
something else. Like, okay, I was very confused.
No, yeah, the collection of points is the complete intersection of some curves in our case.
So this is like a deep projection of complete intersections somehow. Like you're like,
What is a deep projection?
well, it's like you, I don't know.
Oh,
like
oh,
the
yes,
inverse image
yes.
under, I mean, it's like you can study complete intersections, or you can study like these sets that like when you project them, they're complete intersections. And I guess
Precisely.
I'm just trying to
yes.
understand the definition. Sorry for the questions.
No,
Okay,
no, no.
I get it now.
Thank you. Yeah, so when you project those curves, in our case we'll always be projecting onto a plane in this talk because we'll be looking at three-dimensional space. So whenever you're on a plane, you have a set of points as a complete intersection if it is equal to the intersection of two algebraic curves. No more, no less. Equal to that intersection of
So
two
that
curves.
9-point set is Geproci?
It could be the image of a Geproci set. But it is a complete intersection. I suppose in order to be Geproci, you would need to be able to project it down another dimension lower, and then its image would be a complete intersection. So I guess technically yes, but in a trivial way, in the sense that every set of finitely many points on a line is a complete intersection.
Yeah, so in this case.
Yes,
That
so it
makes
would
sense.
be Geproci too.
Yeah, because like 9 points on the peon.
Yeah.
But in general, you could start from a set which is a complete intersection, and when you project it, you mess that up. It's no longer. a
Yes,
complete
yeah, you
intersection.
could in general do that. So maybe that wasn't a good thing to mention about being a trivial case. I'll talk more about the trivial cases in my next couple of slides. First, a notation. Whenever we have can factor z into a times b, z will be a by b Geproci if it's the intersection of a degree a curve and a degree b curve. Yeah.
Sorry, one more question. Are you allowing in higher dimensions the intersection of multiple algebraic varieties?
Yes.
More than two?
Yes, more than two.
Okay.
Yes.
Yeah.
Always exactly the dimension, right?
Yeah, exactly the
Codimension.
codimension.
That's it.
Yeah. Yes.
Wow.
Exactly.
Well, doesn't it depend on the degree of the,
Oh, yeah,
yeah, the
dimension of the
dimensions
space.
of the
Dimension of
spaces
the
that you're
points.
intersecting too, right?
Yeah, the codimension may be given.
Like if they're all codimension 1, then you need that many, but can you allow like codimension 2? Well, I guess, yes, you are, right? Never mind. Yeah.
Okay. Okay. So the first set of trivial cases that we want to ignore are just going to be points in that are already a complete intersection in a plane. So they're in a plane together, and they're a complete intersection in that plane together. No matter how you project it, it's always going to end up being the complete intersection of, well, the image of the blue curve and the image of the red curve. So you can't mess that up being a complete intersection, no matter how you project. The next easy case that we will count as trivial is slightly less trivial, I guess. And it's what's called a grid of points. You have a grid of points if you have two families of mutually skew lines. So in this case, in this image, I have one family, the orange family of lines that are mutually skewed to each other, this black family of lines that are mutually skewed to each other, but they give us 9 intersection points where each black line meets each orange line. This, when you project down onto a plane, will be a set of 9 points in the plane that can be carved out by the intersection of the images of the set of orange lines and the set of black lines. So it will be a complete intersection, and its image in the plane will look something like just that. Grids are relatively easy to understand because it is known that for a sufficiently high family of lines, I think for b greater than or equal to 4, maybe even greater than or equal to 3, but I want to say greater than or equal to 4 to be safe. Your families of lines will always rest on some smooth quadric surface in the plane, so relatively easy to find examples of grids. So the next, or the simplest non-trivial case that we have are what's going to be called a half grid. And that is when the image of the projection will be given by the intersection of a degree A curve and a degree B curve, and one of those two can be realized as a union of lines. So either the degree A curve or the degree B curve can be realized as a union of lines, but the other one is not a union of lines. That makes it a half grid. A nice example that I have is this. I don't have its name on the board, but this is the D4 configuration, also known as the rays configuration. This comprises 12 points that you can arrange 8 of them in a cube like this. One of them is the center of the cube, and the other 3 are over at points at infinity. So I had to bend these lines, but these are supposed to be straight lines toward infinity. That's one realization of the ray configuration. And you can see that you can break down this configuration into 4 families, or 4 lines that each contain 3 of the points of the configuration. And so the image of this configuration, the images of those 4 lines will comprise a component of the complete intersection. That would be the quartic curve of your complete intersection, can be a union of these 4 lines. But the cubic curve won't be a union of lines. Okay.
So in that case,
Yes.
One curve is that 4 lines
Yeah, one curve will be the 4 lines.
with the color, right?
Yeah. So like the red, the blue, the yellow, and the green.
And the other curve is
The other curve will be a cubic curve because this comprises 12 points, which will be the intersection of a quartic curve and a cubic curve. I don't have any illustration about the cubic curve up, but if you flatten this image out in any way, projected it onto a plane and flattened it up, there will guaranteed be a cubic curve that goes through the images of those 12 points, as long as the point that you're projecting from is general. Yeah. And then the least trivial case that we know about, and the one that we have the fewest examples of, really, are non-half grids. And yeah, used to be that only finitely many examples were even known, and still in characteristic 0, that is still the case, that only finitely many examples are known. But you get a non-half grid if the image is a degree A, or is the intersection of a degree A curve and a degree B curve, and neither of them are unions of lines. Okay. So one way to find Geproci sets, or one way to analyze Geprociness, is to start by looking at what are called unexpected cones. So or really just cones over a point that contain your configuration. So here we have the same configuration Z in both images. If we projected from this vertex P onto this plane H, we would get these 4 image points in yellow here. If we projected P onto H, we would get the same 4 image points. If these 4 yellow points are a complete intersection in H, that means that there exists one, in this case, conic that goes through the 4 points, and another conic that goes through the 4 points. So there exist at least 2 conics that go through these 4 yellow points. But if you take the cone of this conic over P, you get a cone that exists in 3-dimensional space. The cone of the conic over here on the right, slurp that up to P, you get another cone that exists in 3-dimensional space. So we can look for intersections of cones that are supported on our scheme Z as a way of looking for Geproci sets, especially if, particularly if we allow the vertex of our cones to be general. If P is general, that means that we can take our configuration of points and create a cone that has a vertex wherever we want. And if we can contain, or if we can have multiple cones that have vertices wherever we want, then when we take a general plane H and intersect both of these, what we will end up with is a complete intersection of where this blue cone intersects H and where this pink cone intersects H. So looking at these cones is very, very connected to the Geproci property, and it'll be a useful tool. But first, what I wanted to do for my dissertation is I wanted to take this Geproci search into the positive characteristic setting. Geometry gets pretty weird when you have positive characteristic, and you get some types of configurations that simply aren't possible in characteristic 0. With these new algebraic tools that we have. We have the freshman's dream, and we have Fermat's little theorem. And it turns out that this weird geometry ends up making Geprociness quite natural and positive characteristic in a way that it just isn't in characteristic 0. So for example, let's just take all of 3-dimensional space over a finite field. If you take all of 3-dimensional space over a finite field, that's finitely many points. Is that Geproci? Well, if we break down the number of points there are in 3-dimensional space, in a field of size q, we can factor that as q plus 1 times q squared plus 1. So if we wanted to see if it was Geproci, we could look for these cones of degree q plus 1 and degree q squared plus 1 that contain every point in our three-dimensional space over a finite field and has a vertex, well, at a general point. And if we can't include any point in here, then we'll take a field extension. I'll choose to take just the algebraic closure. So the vertex of our cone will be somewhere existing in the algebraic closure P3. And it turns out that this cone is relatively nice to write down. In fact, yeah. Yeah.
So that said, there is a cone containing Z, but
A cone containing Z, yes.
cone in where?
In P3 over K, where K is the algebraic closure.
Okay, I see.
Yeah.
Okay.
Okay. Yeah, so you can really write it formula down as this nice sort of determinantal formula. And we can see, a little evidentially that this cone must contain Z, because if I, say, plug in any point in our field of size Q in for X, Y, Z, and W, Fermat's little theorem says that X to the Q is equal to X. If we have a field of size, these are elements in our field of size Q, so we'll have a repeated row, so that way we can see that this cone must contain Z, and we can also see that, this cone is indeed supported on the vertex P, because if we plug in A, B, C, D in for X, Y, Z, W, we'll get a determinant 0, we'll have 2 repeated rows. Proving that the cone has a singularity of multiplicity Q plus 1 is a little bit trickier, so I won't go into that, but we can kind of see so far. The degree Q plus 1 cone is not as interesting, so I want to move on to this next cone. This opens up a whole lot of doors. The next cone comes from a concept in combinatorics called a spread. A spread is a partition of a space, so in this case, if we have three-dimensional space, is a partition of three-dimensional space into a collection of lines that are all mutually disjoint. So you have, for example, if we go back, there are q plus 1 times q squared plus 1 points in our three-dimensional space. Every line over a field of size q contains q plus 1 points. So we can divide up, we can partition our whole three-dimensional space into a union of lines, q squared plus 1 many lines, each of which contain q plus 1 points. That partitioning is called a spread. And spreads can even be founded not just in finite fields, but even over the real numbers. Something that really interesting that my advisor told me was, it turns out that the hop vibration provides an example of a spread. The hop vibration is a map from S3 down to S2, where every fiber is an S1. S2 is equivalent to the projective line over C, and you can map S3 down to P3 over R by gluing antipodal points together. And so this hop vibration factors into this antipodal map plus this map F. The fibers along this map F are going to be, well, S1s, which in P3 are the same as P1s over R. So this, the fibers of this map F provide a partition of P3 into a set of lines as well. But back to finite fields. We can partition this space into q plus 1, or q squared plus 1 lines. And then, when we have that set of lines, we can form a cone by joining them each with our general point P. So if we have a line here, we have our point P here. We can form a cone. It's just a union of planes that contain our line and our general point P. So this tells us that we have our q squared plus 1 cone down. We have our q plus 1 degree cone down. And so when we project down into a plane, that image of the, or the intersection of the plane with our q plus 1 degree cone forms a degree q plus 1 curve. The intersection of this cone, which is really just a union of planes, with this P2, forms another curve, which is really just a union of q squared plus 1 lines. The image of Z will be the intersection of that degree q plus 1 cone and the degree q squared plus 1 lines, meaning that P3 over a finite field is in fact Geproci, and we can classify what type of Geproci set it is. It is a half grid. I don't know if I have that actually written down, but it is a half grid. And we get new sizes of Geproci sets, of non-trivial Geproci sets too, that aren't possible in characteristic 0. For example, it is known that there are no non-trivial 3x5 Geproci sets in characteristic 0, but if you take q equals 2, then there is one. Okay. So looking at all of these spreads got me really interested in reading more about what the combinatorists were doing with these objects and how they could apply to what I was looking at. That led me to reading about what are called partial spreads and maximal partial spreads. So a partial spread with deficiency D is a set of q squared plus 1 minus D mutually skew lines. So you have some lines, but you don't have all the lines. A maximal partial spread will be a partial spread of positive deficiency that is not contained in any larger spread. So at first glance, it seems like a maximal partial spread is kind of like a dud, like you were trying to build a spread, but somewhere along the way you made the wrong choice for a line somewhere, and now no more lines will fit, but you haven't covered all the points. That's how I first thought of them when I was trying to find examples of spreads, and I kept failing. But maximal partial spreads, I learned eventually, are pretty interesting in their own right. Maybe not because they themselves are interesting, but their complements are interesting. Those points that you couldn't quite grab by choosing lines. These maximal partial spreads provide a way of giving us infinitely many non-trivial Geproci sets, and in fact, many of which are also non-half grids. Because if you take the complement of a maximal partial spread with deficiency D, you will get a q plus 1 by D Geproci set. And I'm using these squiggly brackets to denote the fact that we don't necessarily need to apply that D is greater than or less than q plus 1. That's the deal with this squiggly bracket notation. The parentheses notation, remember, was only for if A was less than or equal to B. And furthermore, when D is greater than q plus 1, this complement will be will be forced to be a non-half grid, which is great news because we already have some bounds from Hedden in 1993 and 2002. One paper proved one bound, the other paper proved the other bound, but I forgot which one was which. That when q is greater than or equal to 7, we can bound D between these two numbers. So this inequality will always be satisfied for some maximal partial spreads for q greater than or equal to 7, giving us infinitely many examples of non-trivial, non-half grid Geproci sets. again, beforehand we only knew about finitely many examples. Okay. These Geproci sets in positive characteristic setting aren't just contained, it seems, to the positive characteristic. They share many properties, or at least some of the examples that I've come across share many properties with examples of Geproci sets that we've already known about for a while in characteristic 0. For example, we found one maximal partial spread in characteristic 7 whose complement is a set of 40 points over P3, in P3 over a field of size 7, that turns out is a 5x8 Geproci set, and it's a non-half grid. And it shares a lot of properties in common with do I have it written down? The Penrose configuration. I don't have it written down on this slide. It's the Penrose configuration. It exists in characteristic 0. It's a set of 40 points that is also 5x8 Geproci. And so that's in characteristic 0, only one non-trivial Gorenstein configuration is known. That's the Penrose configuration that I'm talking about. It is also a Gorenstein configuration. Did I mention that? The same as this configuration. So it seems to be there is some likeness between some of these things that can be found in positive characteristic and some of these things that we already know about in characteristic 0. So one direction that I like to go in is further cementing that relationship between perhaps finding more fascinating examples of Geproci sets in positive characteristics, maybe characteristic 9 or characteristic 11, and seeing, do we get anything new back in the characteristic 0 setting that has similar properties as that? Okay, so that's enough of the positive characteristic talk for now. I'll come back to it later, but first I need to talk about another direction that we were thinking about with these, finding new examples of Geproci sets. And that is considering non-reduced schemes. In other words, what if some of the points in our configuration were the same as other points in our configuration? In other words, infinitely near points. If you have a point P, then Q is infinitely near P if Q is located somewhere on the exceptional locus of the blowup at P. Intuitively, I always think of Q represents some tangent direction, some direction at P. Technically, Q is not strictly speaking an element of X. It's an element of it's a point on the blowup of X. But I like to talk about them as if they were just points on X itself. So I'll talk about things like, I'll have a configuration of points. One of my points is P, the other point is Q, and Q is infinitely near P, representing this direction. That's how we'll talk about this. So, for example, let's go back to characteristic 2. If we have this set of 6 points, a non-reduced scheme of 6 points, 3 actual points, and then 3 infinitely near points. So each of the 3 points counts twice. That's what I'm using with this notation right here. Then this set of points considered as a scheme is also a 2x3 Geproci half grid. for example, if you project this set of 6 points down onto a plane, these 3 points, or these 3 infinitely near points, are all pointing to the same point. And so in the image, you will get 3 points and 3 infinitely near points that are also all pointing at the same point, like this. So this set of 6 points, counting each of them twice, is a complete intersection in characteristic 2. In characteristic 2, every tangent line on a conic, there is one point on the plane that is contained in every tangent line in a conic. And characteristic 2 is the only place where something like that happens. And so you will be able to find a conic that goes through all 6 of these points. And by going through all 6 points, I mean it contains the 3 real actual points. Can't say real because it's not technically real. And has the appropriate tangent lines at each of these points as well. In no other characteristic will you be able to do that. So there is some, I don't even know how to draw it, but there's some conic that goes through all 6 of those points. And we can find a cubic through all 6 points simply because 9 points uniquely determine a cubic. That fact remains true in positive characteristics as well. And it is a half grid because one of the cubics that you can choose can simply be this union of lines. This is technically a cubic that goes through all 6 points. So it is a half grid. You can find an interesting non-half grid by changing it slightly. Here we have 4 points on a tetrahedron in characteristic 2 again. And this time I'm choosing a 5th point, I'll call it the center of the tetrahedron, where you have 4 infinitely near points. Each of them are pointing toward this center point. And then that center point is the only reduced point of your scheme. So in this case, when you project, you will end up getting 5 actual points and 4 infinitely near points, each of them corresponding to the direction toward the reduced point. In characteristic 2, there exists a family, a pencil of cubics that is supported on this non-reduced scheme, and only in characteristic 2. This is what's called in fact, this pencil of cubics has an interesting property in that it is a quasi-elliptic fibration. An elliptic fibration is, a P1 of cubics. A quasi-elliptic fibration is a P1 of cubic curves, but each fiber, each cubic in the pencil is singular, and it is in fact cuspidal. You can use an Euler characteristic argument to show that quasi-elliptic fibrations don't exist in characteristic 0, and in fact they do only exist in characteristics 2 and 3. But this specific configuration is only supported on a quasi-elliptic fibration in characteristic 2, I found. I have not found really any Geproci sets so far of non-reduced schemes that are actually Geproci in any characteristic other than 2. So the 2 examples that I've just shown you are pretty much it for studying infinitely near points and non-reduced schemes and studying their Geprociness. think, yeah, that's all I have for my talk. I have some future questions that I'd like to explore more of this on. Some of them I've already talked about, like higher order infinite linear points, or working on higher order infinite linear points in any characteristic other than 2. Especially characteristic 0. A little surprised that there doesn't seem to be any luck in the characteristic 0 setting here so far. But yeah, these last 2 questions are new as of a couple weeks ago. Generalizing Geproci configurations that we know about into higher dimensions to finally find something that's interesting in Geproci in P4 or P5, for example. And another idea that I think Chris had was looking for Geproci sets in not just projective space, but in Grassmannians in general. In Grassmannian spaces. But yeah, that's all I have.
Questions. So these, so I guess some of the trivial example of Geproci sets that you said, I can see how you can actually sort of vary them continuously, right? Because if you have like 2 curves in a plane in 3-dimensional space, I can move one of the curves so I can get a continuous family of Geproci sets.
Yeah.
But the interesting examples, do they tend to be discrete, or can they also vary? If you have a Geproci set, can you wiggle some points, or can you try to wiggle one and then the others are forced to wiggle in some way?
I think the D4 can be wiggled. Well, if you wiggle one point, the other ones will be forced to wiggle in some way. But yeah, you can make like a family of D4. So all be isomorphic to each other. Like under isomorphisms of P3, you can vary them. But with the non-half grids, like the Penrose configuration, I'm not sure if you have very much wiggle room with those. I think those, I have a feeling, are more discrete, but I haven't really thought about it.
So you know, I mean, if they give sort of like interesting subvarieties of the Hilbert scheme of points of P3, something like.
Sure. One thing that my my advisor Brian Harborn's other students have been working on were not Geproci sets, but surface Proci sets or curve Proci sets, where the general projection may not be a complete intersection, but if you project from some surface, you'll get a complete intersection, or some curve in P3, you'll get a complete intersection. I don't know if that's related to, but yeah.
There was this interesting thing with this Weddell surface.
The Weddell surface, yeah, that's what Allison was working on.
You take 6 points, 6 general points in P3, you project them down, they're not going to lie on a conic, but it's a codimension 1 restriction to get the projection to lie on. And so if you look at the locus of all points, which will project down such that the image lies on a conic, that forms a surface called the Weddell surface. Okay. And but it's also connected to this Kummer quartic, which is this quartic surface that has 16 singular points, which there's the largest number of isolated singularities that a quartic can have in P3 is 16. We realize that, and somehow it's connected to this problem as well. It's like a dual objectives. Anyway, that would be an example of one of these surface, like 6 points, you get the surface.
And it's an algebraic surface.
Yeah.
Yeah.
What is like a motivational background? Why?
Well, this whole search for Geproci stuff started as a result of a Stack Exchange question posted in 2011. Someone asked on Stack Exchange if such a configuration of points existed, the word Geproci didn't exist yet. And I think it was one of the authors of this paper who answered it first, either Cantini or Migliore. And then it kind of built up. They found the examples of grids first, and then it kind of built up and roped in more people, and but other than that initial, like, to answer a question on Stack Exchange motivation, a deeper motivation might be, I believe that this question is related to the Lefschetz properties. I think that is mentioned in this top paper right here, the configurations of points in projected space and their projections. I believe there's some kind of connection with the Lefschetz properties, strong Lefschetz and weak Lefschetz, but I'm not exactly sure what the connection is. Yes?
I see the end queen problem.
Yes.
So is it somehow connected with placing queens on a board if they're non-attack?
Yeah, yes. Yeah, setting up queens on a board or a modular chessboard so that they're not attacking. Hedden discusses that in his 2002 paper and his 1993 paper, where those bounds came from. It turns out that spreads, yeah, here, 1993 to 2002, spreads can be understood. I forgot the exact connection between the modular chessboard and spreads, but one way that Hedden was constructing maximal partial spreads was to think of maximal partial spreads as a solution to the end queen problem, setting up where each queen on the chessboard represents a line, and the queens not attacking each other represented the lines being disjoint. And I forgot exactly the exposition behind that. The exposition behind that connection, but yeah, it exists. Very cool combinatorics type connection.
I guess there's one more motivation, I think that seems to be connected to these things, and is like the D4 example, which was there's these 12 points in P3, and if you do a general projection, you get a complete intersection of type 3, 4. If you take the cone over the cubic that you projected from, we get a very singular cubic surface. This cubic surface will be an element of the cube of the ideal of the cone point. And the cube of the ideal of the cone point in P3 should impose 10 conditions. It's a scheme of degree 10. It should impose 10 conditions on things. But if you do a count, there shouldn't be, if you took 10 general points, you're not going to be able to find a cubic. Because there's an object that exists, like you take the ideal of these 12 points, and then you intersect it with the cube of an ideal of a general point. There shouldn't be any cubics around, but there is a cubic. Like if you do a dimension count, how many conditions you're imposing on cubics, you get 10 plus 12, you get 22 conditions on cubics, but there's only 20 dimensional family of cubics. There shouldn't be any cubics around in this idea, but there is. And so there's a connection with unexpected existence. The linear system's not the right size.
So one way to figure out enumerative problem using this configuration, right?
The what?
So this thing gives us some answer to some enumerative question.
Yeah, there's this general question that that's floating around that Rick Miranda's done a lot of work on, was you know, there's this famous example, it's this Alexander Hirschowitz theorem. And the first case is, you take a point in the P2, and you take its square of its ideal, you get a scheme of degree 3. You take another point in P2, you take its square of its ideal, you get a scheme of degree 3. So together their union is a scheme of degree 6. And there shouldn't be any quadrics. There's 6 quadrics in the plane, and you shouldn't be able to find a quadric going through 6 general points. But if these things are these fat points, well, you take the line through the thing, through the 2 points, and you square it. And this is, it's a simple thing, but this is related to this statement about you take the Veronese embedding of P2 into P5, you do a general projection. Most of the time, if you take a surface in P5, you do a general projection, you get something that has singularities. But a general projection of the Veronese surface of P5 is smooth in P4. And it's related to this, it's related to linear systems questions, and all these things are kind of related.
No more questions or comments? Let's thank you again.